Hello everyone and welcome to another video. So today I'd like to have a quick discussion to talk a little bit about how to translate inputs, outputs, and initial conditions between two different types of systems, namely a linear dynamic system and a nonlinear dynamic system. So this is going to be a fairly short discussion, so don't get too comfortable, and the only reason is because we've done a lot of work to build up to this point in previous videos. So we're going to talk a little bit about setting the stage about how to get here, as well as some quote-unquote, prerequisite videos that I'm assuming everyone has watched before joining in with this discussion. So to set the stage for this, really what I want to talk about is if you have a nonlinear dynamic system, what's the workflow that we typically follow when trying to do analysis, control design, simulation, all of that kind of stuff to get a linear system, and then how do we take some of those results and tools and products that we build based on linear systems and then come back and apply it to the overall nonlinear system. Okay, so that's a very high level approach. So maybe let's diagram this out in terms of, like I said, kind of a workflow of how this typically happens. So what we usually do, right, is we start usually with a nonlinear system, right? And again, I'm just going to call it a nonlinear system, and we understand it's a nonlinear dynamic system, right? And the idea is that its dynamics are governed by something like x dot of t as some function of the states and the controls, right? And then the output of this system might be some other function of the states and controls. So again, this is just your standard nonlinear state space representation of a system. And again, what I'm going to probably do while we're talking about the workflow is at each of these stages, I'll try to flash up some videos over on the other side of the screen talking about where you can find more information if some of these concepts or ideas are unfamiliar to you. So again, we've got a nonlinear system with inputs u and outputs y, okay? And I'm going to try to be very explicit about the notation in this discussion. So remember, the inputs for this nonlinear system, I'm going to call u, the outputs are going to be called y. Okay, now what do we typically do once we have this nonlinear system? Well, the next thing in our workflow is usually you may want to try to trim this nonlinear system and find an operating point or an operating condition about which you would like to do some analysis. So the next step in this process is typically you're going to trim the system. Okay, and what that produces, right, is the idea with the trim process is you're finding these states, let's call it x naught and u naught, right? So this is usually your trim point or your equilibrium point. So I'm going to call it trim / equilibrium point. All right, and again, we talked about the differences between these and some of these videos you're seeing playing on the other side of the screen, right? So hopefully you now understand what is a trim point and a / equilibrium point, right? So once we have this operating point, right, the next step in the workflow was then, okay, we want to now linearize this nonlinear system about this trim point, right? So the next step was the linearization process. Okay, now the idea with the linearization process, right, the entire goal was we wanted to end up with an approximation of this nonlinear system around this trim point, and that is going to be what is referred to as typically your linear system, right? This is your linear time invariant or your LTI or your state space, your transfer function or your linear system, linear dynamic system, whatever you want to call it. The idea here is that this system behaves very similarly to the nonlinear system, but only near this point, right? So the idea was, this is where we got to be a little bit explicit about the notation, right? We talked about this again in our linearization video of what this is doing, right? But the dynamics here are going to be delta x dot, right, is equal to a delta x plus b, let me make this a little bit wider so I don't have to cram this all in, plus b times delta u, right? Okay, and the output, delta y, is equal to c times delta x plus d times delta u, okay? Okay, so again, this linear system has inputs now of delta u and has outputs of delta y, right? So again, remember our discussion on what these deltas meant, right, is we defined the perturbations from this trim point as something, for example, delta x, right, is basically where the state of the system is and how it minus the trim point. So this is how far the state of the system has moved from the trim point. And we define that as delta x, right? And similarly, delta u is also just going to be u of t minus u naught, right? So this is the idea of perturbations from trim, or this linear system is basically describing and measuring how the system operates near this point as you move away from these locations, right? Now, the one thing that we probably should mention is a couple of things, just for the sake of completeness. One thing that we maybe should think about is this Y signal. So the trim point of the equilibrium, right? It's the trim states and controls. But if you plug this into your equation, right, this also kind of generates sort of a Y naught, right? The Y naught is just simply G of X naught and U naught. Right? So this is basically like the trim output of the system, right? It's, yeah, the output of this system at this trim point, right? So using this, we also can define a similar concept of, you know, a delta Y could be the actual output of the system and how far it deviates from this Y naught location, right? Okay, so now I think we've got all the signals defined. And again, the thing I'm being explicit about is the notation, right? So the idea is when you do linear analysis down here, or you analyze a linear system, you're really trying to understand, or you're simulating, or you're doing analysis of how the overall system operates near this point. And you are actually, this thing is describing perturbations from the trim point, right? That's what that capital delta is, okay? So the thing that makes this confusing is usually in a lot of literature, people get lazy and they drop this notation of capital delta because they don't want to be writing capital delta all the time. So a lot of the times you'll see your linear system written like this, right? It's just going to be x dot is ax plus bu, y is cx plus du, right? So a lot of times they'll drop this delta notation and you'll see something like this, and this looks totally familiar. And if all you're doing is just doing linear analysis, that's totally fine, right? If all you care about is simulating and understanding how this linear system behaves, yeah, we don't need to necessarily worry about what that capital delta meant, right? The place where it gets interesting is if you do linear analysis down here, you got to remember this linear system, it came from this overall nonlinear system, right? This might be your high fidelity, complicated system that you actually want to control, and you are doing design and control design and analysis based on this linear system. So you really have to be able to take the results you have down here and translate it back up to apply to the nonlinear system, okay? Now, in that case, this is where you can get into trouble if you drop this capital delta notation, or if you're just not careful of what's going on. We really need to remember and keep in mind that this signal U is not the same signal that goes into the nonlinear system, right? Same thing, this state X is not the same as the state X of the nonlinear system. So this is why I'm advocating for this discussion. Let's keep these capital deltas everywhere so we can explicitly see how these signals are different, right? So now it's very clear that delta U is not the same thing as U. And we can see that again from our equation right here. Here's the relationship between what is delta U, which is again the input to your linear system, versus U, which is the input to your nonlinear system, all right? Okay, so the reason we care about this is going to come up, and why don't we look at 3 cases or 3 different scenarios you might run into where you might need to worry about these differences. So scenario 1 is obviously, if you think about this, if you're computing or using inputs, where did I write this down? Right, yeah, here, inputs, U of t, right? So again, you see it down here, U and delta U are different, okay? And we're gonna look at how that is, that manifests itself. Oh yeah, obviously the other scenario is like, let's look at the other side of this, right? Is when you're computing or using the outputs of the system, right? So if you're using these signals out here for signal measurement or for control design or for sensor feedback or anything like that, again, we got to be careful. What's the difference between Y and delta Y? Right? And then lastly, scenario 3 is, what about initial conditions? What if you are computing or using initial conditions? right? So that is x of 0, okay? And again, let's be very explicit here. This x of 0 is the initial condition. X naught is something completely different, right? X naught is the trim location, or the equilibrium point, wherever you decide to do your linearization. So again, let's just be explicit here. I'm going to call it out. X naught is not the same thing as x sub 0, right? This thing over here is your trim state, right? Whereas this notation means your initial state, right? Okay, so if that sounds good, why don't you give me a second to erase the board and let's look at this scenario 1. Okay, so with scenario 1, the idea is, again, you got to remember how we got here and what your typical workflow as a control engineer or a simulation engineer is going to be, right? So a lot of times we do a lot of our work down here, and let's call this, quote unquote, linear land, right? You're working with the linear system. So you've got your linear system down here. So I'm just going to call this linear system, right? Okay, and you are going to, one of the first things that, you might do if someone drops a linear system in your lap is you might go ahead and say, oh, I know, let's just input some signals to see how the system responds, right? This is basically what human beings do, right? You get something new, we're going to poke it with a sharp stick and see what happens, right? That's exactly what you're going to do here. You're going to inject signals into this. You're going to shake the thing, you're going to poke this thing with some sharp sticks and see what comes out the other side, right? So that's totally reasonable, right? So you might go ahead and do this, hook this up to a scope or something like this. So here's your linear system, here's some kind of input, right? You put a step input, you put a sine wave, you put, ramps, you do whatever, right? And you see what comes out the other side, right? Now, that's totally great. And let's say this is all working nicely, and now you say, oh, well, what if I want to use this same input, and instead of jamming it into the linear system, what if I want to see how that responds to or how the nonlinear system behaves, right? It's the same thing. You would want to kind of do the equivalent shaking or poking or whatnot, and hopefully what happens is, you put this into another scope, and hopefully these two things are similar. Right? That's the idea, right? If the linear system is a good model of the nonlinear system, you put in the same inputs, you hopefully get very close to the same outputs, right? So one common thing to, you might be tempted to do is say, oh yeah, hey, just put that in, right? I'm going to use the exact same signal into both of them and they should be the same. Well, this is not going to work, right? And the reason why it's not going to work is because the inputs to these two systems are not the same. And this is where I always tell anyone who will listen that one of the things that I highly recommend doing is label all the signals in your block diagram, okay? So again, the linear system, we know it has inputs of delta U, right? Okay, and has outputs of delta y, right? So the first thing you got to think about is the nonlinear system has inputs of u and outputs of y, right? Okay, so now what you might want to think about is, well, okay, how are u and delta u related to one another? As you can kind of see right here, delta u is u minus u naught. So really, this is the exact same thing as, well, I'll tell you what, let me write this out, right? We said delta u is u minus u naught, right? Or the other way you could say this is u of t is delta u plus u naught. Would you agree? Right? So really, if I want to use this same input that I'm jamming into the linear system into the nonlinear system, you actually have to go here and we have to add back on u naught, right? So now the signal coming out of here, this is delta u plus u naught, which is the same as u. So now, if you input this into this nonlinear system, now you have an equivalent sort of setup, right, where both of these things are being input, right? And you know what, while we're looking at this, maybe we should we could probably knock out scenario 2 at the same time with this exact same block diagram, right? We said scenario 2 was when we were looking at y of t. So same thing. You might be tempted to now put both of these into a scope and compare them, but again, you see there's a discrepancy between y and delta y, right? So again, we do the exact same trick down there. We now need to actually, if we want to compare apples to apples, what we may want to do is take this nonlinear system, and now what we're going to need to do is we might have to, let's see this, it's y, this signal is y minus y naught. So we need a plus minus. So if this is y naught, right? Coming out of here, this is sort of like a delta y from the nonlinear system, right? So again, sorry, this is a little bit ugly, but I think you get the picture, right? You need to translate between these two signals. They're different by this offset, right? So if you want to plot both of this signal and this signal on the same graph, this makes more sense, right? Because now you can go ahead and, like I said, yeah, compare sort of apples to apples, right? Okay, so, yeah, I guess that's scenario 1 and 2. It's pretty simple, right? And you can see really all we're doing is basically just implementing these equations here in our signal flow diagram or in your control system architecture or what have you, right? Okay, tell you what, give me a second to erase the board and let's look at scenario 3. All right, so let's now look at what to do with initial conditions between the linear and the nonlinear system. So again, starting down here with the linear system, I've just kind of expanded it out just to show, you know, in a signal flow diagram, what the dynamics of x dot is equal to ax plus bu, y is equal to cx plus du would look like. And again, just as I said that, you can see I dropped the delta notation, which I told you I wouldn't do. So bad mea culpa, that was my fault. And as you can see, this is why a lot of people just why it's very easy to drop that delta notation, but again, we're trying to be explicit about that. So I have been explicit by labeling all of these signals, right? Now, the thing we need to pay attention to is the integrator here, right? The integrator is the thing that's going to have initial conditions, right? So inside this linear system, right, the initial condition that goes in here, right, is going to be actually delta x at time 0, right? That's the initial condition that you put into this integrator, right? And this will simulate your linear state dynamics with an initial condition of delta x 0, right? Now, again, you might want to do the exact same thing up here, right? You said, okay, I've got a linear system, I'm going to put some non-zero initial conditions into here, and I'm going to see how this thing responds, right? Now, if you want to then do the equivalent experiment up here in the nonlinear system, you also got to think about what's the initial condition that goes into this integrator right here, right? And again, this is where labeling all the signals explicitly is going to save your bacon, right? So you can clearly see that the initial condition of this integrator is actually x at time 0, not delta x at time 0. So now we got to ask ourselves, what is the equivalent initial condition, right? So again, all we need to do is come back to our definition of what's the difference between the perturbation and the absolute signal, right? So again, if you just solve for x of t, you see that x of t is really just delta x of t plus the trim amount, right? So this perturbation that needs to go in here, it's actually delta x at time 0. Basically, it's the same initial condition that you stuck into the linear system, but you have to add on the trim, the trim state. Right? So there you go. Again, this is actually a pretty simple discussion. Again, all we're doing is just basically implementing those equations and keeping track explicitly of what signals are deltas and which ones are not, right? Okay, so tell you what, let's erase the board and let me show you a more comprehensive usage of why you might care about this. All right, so where does this come into play in sort of a quote-unquote real-world scenario? So down here, hopefully this type of a block diagram should look super familiar to you, right? This is what we typically do with linear control design, right? We start with a linear plant, we do whatever analysis we need to on its poles, its eigenvalues, its performance, bandwidth, you know, what have you, and we design a linear controller to control this linear plant. And we can come down here all day designing these linear controllers. This can be a PID, an LQR, full state feedback, you know, it really doesn't matter. There's a whole wealth of tools, an enormous literature on how to design linear controllers for linear plants, and we can provide all types of guarantees about the performance of this overall system, right? So as long as you live down here in, again, we called it linear land, right? You stay in linear land and everything is happy and hunky-dory, right? You can do this all day, right? The only problem is, again, you got to remember where we came from, right? it's nice to play down here in linear land, but we came from nonlinear land, right? We started with a nonlinear system, so ideally what we would like to do is take the results we have down here and move it back up and apply it to the nonlinear plant, right? So again, you have your simplified system where you can design this controller, but really what you care about is this controller controlling the nonlinear plant. This is the actual system you want to control, right? And have it have the performance that you desire. So really what we need to do is we need to bring this system up here, right? And now you can kind of see why we were explicit about all these deltas and whatnot, and why we had those discussions on those previous 3 scenarios, because you can't just simply unplug this controller and plug it in up here in the same fashion. It's just not going to work, right? Because we have to take into account the fact that the linear controller is working on a linear system and is working on perturbations from the trim point, right? So again, I've explicitly labeled all these signals with the deltas down here, so we can clearly see that this linear controller, it expects inputs of delta y, and it will spit out outputs of delta u, right? So in order to take this linear controller up here and make a nonlinear controller, we have to reconcile the differences between the deltas. So the first thing I'm going to do is, sure, let's go ahead and bring up this linear controller. So literally, let's grab this thing and we will just go ahead and jam it into our block diagram up here. The exact same thing. So literally, copy, paste. It's the same thing. Except now we know that coming out of this is delta u, and what it expects is delta y. Right? So now we can basically use those scenarios we talked about previously to get these signals lined up. So you can see, don't be silly and directly connect this line. This is delta u. The nonlinear plant is expecting u, right? So we need to go ahead and do our little trick we did earlier of basically adding back on the trim control, u naught. Right, did I get that right? U is delta U plus U naught. Yep, okay, that's correct. And same thing over here. We can't simply just feed back the sensor measurement and plug it in here, because this signal is y of t, right? And the controller is expecting delta y. So again, all we got to do is we now need to subtract off the trim value, right? So now we need to come in here and go plus minus in this case. This needs to be now y naught, right? Now, if you take this thing up here and, well, I'll put this in maybe sort of dashed, right? So the linear controller in combination with the trim points, right? This gets us our non-linear controller, right? And again, the thing we also want to remember is if this thing has states, right, and as we have kind of implied by the way we wrote it as C of S, right, so there may be states or integrators associated with it, right, we need to go ahead and make sure that the initial conditions of this are set equivalently to down here, and same thing with the plant, right, we just talked about how to set the equivalent initial conditions between these two systems, right, so this hopefully gives us a rough idea of of how to theoretically make sure that we are translating between nonlinear and linear systems, and we're computing their inputs, outputs, and initial conditions appropriately, right? So again, that's our abstract discussion. Tell you what, let's look at a numerical concrete example of how this works. All right, so the example system I'd like to look at is, I have a model of a nonlinear rigid 6 degree of freedom aircraft model. Sometimes it's referred to as the Research Civil Aircraft Model or RCAM model. And we've done some work here on the channel to talk about trimming this model and linearizing it. So this sounds like a great example. Let's use this trim condition of straight and level steady state flight at 85 meters a second. So the aircraft is just cruising along at 85 meters a second, as you can see here, with no angular rotations, and it's just got a little bit of nose up, 0.015 radians of attitude up. And again, here's the trim controls that get us that flight condition, right? So no aileron, you actually have a negative elevator of, negative 0.178 radians, no rudder, and then, a little bit of throttle to get you cruising along at that speed, right? So here's the nonlinear model, and we linearized it and got a linear model around this operating point. So now why don't we jump over to Simulink and let's just simulate a bunch of these conditions of, you know, non-zero initial conditions? How about some elevator input doublets where we kind of pull back on the elevator and then push down on the elevator and let it go? And again, the goal is to do it both in the linear system and then apply that exact same equivalent condition in the nonlinear system and see how they stack up. So let's jump over to Simulink and do that now. All right, so let's take a look at this Simulink model that I've built. So again, we've got the nonlinear aircraft model up here. And again, if you look under the hood, this looks exactly like we talked about earlier. And as you would expect, you know, you've got the integrator going from x dot to x, and in this case we're going to use the output as just the full state of the system, so y is equal to x in this case. But if you had an extra output equation, you could obviously jam it in here, but to keep things simple, let's just assume that the input is u, the output is y, which is the same thing as the entire state of the system, right? And then down here I've got the linear model, which again is our linear state space system, but now this has an input of delta u and the output is now delta y, which is the same thing as delta x, as we've just already said. And now what I'm showing here is the translation between the linear and the nonlinear model as we've discussed above. So the only difference is the difference between the trim input and the trim output, right? So all we're doing is adding or subtracting appropriately to kind of make sure that we have the appropriate signal going into each of the different systems, right? So again, you're living down here in linear land, and let's go ahead and do a couple of experiments. So the first experiment I think to do would be to just let these things run. So we're going to make this input delta u be completely 0. So if I come over here to my MATLAB script, let me go ahead and just make sure I've got that set up correctly. Let me uncomment this here. Okay, so steady state. So in this case, you can see that there's not going to be any doublet in the elevator. So in this case, maybe we should just jump back to the Simulink model real quick and show you how I have this thing set up. So I've got this set up so that the input to the aircraft model is basically just a doublet, or, you know, an up and then a positive value, then a negative value, and then 0 in the elevator channel or the horizontal tail, right? So all the other inputs are 0. And again, these are delta U1. This is delta aileron, delta elevator, delta rudder, delta throttle 1, and delta throttle 2. So really what we're trying to do is we're going to try to simulate just putting in an elevator input of a desired magnitude and a desired duration. And again, I've got a scope hooked up here so we can look at that later. But for now, for this really simple system of steady state, notice I'm making the magnitude 0. So basically all the inputs are 0, right? And all the initial conditions are also 0, right? So, and again, this is the initial condition for the linear system, right? Now, the nonlinear system, right, if we come up here and look at the nonlinear model in the integrator, as expected, it is the initial condition of the linear system plus the trim state, right? So again, I load those values in here, and I think I've already loaded them. Yeah, so as you can see, here's the trim state. So the aircraft is flying, it's 85 meters a second, and you've got some nose up, right? So again, the input is non-zero, or sorry, the initial condition for the nonlinear system is non-zero, even though the initial condition for the linear system is completely 0. So if I run this, hopefully if we have all the signals set up appropriately, they should be equivalent. So again, let me pull this down. And let's look at the inputs. And again, you can see, yeah, the inputs make sense, right? They line up with one another. Okay, and then let's look at the outputs of the system. So in this case, notice we should be explicitly calling out what we're plotting. So I'm plotting U, V, W, P, Q, R, or in other words, X1, X2, X3, X4, X5, X6, X7, X8, X9. Not delta X1, delta X2, right? These are absolute values. So that's why you see X1 or the forward velocity hover near the trim value of 85 meters a second, right? Which was over here. If we look at, whoops, come on, hit enter. There we go, right? So you see that the trim first state is 84.99 meters per second. That's the forward velocity. And yes, you can see that the nonlinear model hovers near there. The linear model, after we add the trim state back on, we also have that equivalent signal here. So again, all this looks very reasonable, right? Of course, you can say that these nonlinear models, why are they wiggling around? But if you look at the magnitude of all these, they're very small, right? The magnitude is 10 to the minus 8, 10 to the minus 9. For all intents and purposes, right, the vehicle is floating along perfectly straight and level and in steady state. And the linear model is numerically identically equal to 0, because that's the beauty of having a linear model, right? Is if we set 0 initial conditions with 0 inputs, you expect an absolute 0 output, right? Okay, so this is great. This is looking pretty good. Why don't we go ahead and now change the input to this doublet, right? So now in this case, in this situation, let's input it looks like a 10-degree elevator up and 10-degree elevator down for 5 seconds, right? So that's what we're going to do. And again, let's use 0 initial conditions and see what happens. So again, let me run this. Which is going to call the Simulink simulation, and let me go ahead and let's go look at this delta signal here. So here, let me open up the scope if I can get this to open over here. Okay, great. Here we go. So take a look at this, right? So again, you see this goes elevator up for 5 seconds and then elevator down for 5 seconds. So again, we got to be a little bit careful what this signal here is. This signal is delta U2, right? Or delta elevator. This is the change in elevator position from the trim location. So this is when it's at 0, you're basically saying keep the elevator at trim, and then add 10 degrees, and then go negative 10 degrees from trim, and then go back to trim, right? So again, this signal, what this scope is hooked up to is the delta signal. Right? The reason I bring that up is if you look at the trim control, right, that's the second one, U2 sub 2, and let's convert this to degrees, right? So let's go rad to degrees of answer. So actually, look at this. The trim position of the elevator is actually negative 10.2 degrees. So even though we're putting in a signal here of delta of positive 10 to negative 10, actually, in the nonlinear simulation, the elevator will never ever go positive, right? So we can see that by looking at the traces of the absolute signals, right? So again, here we're plotting U1, U2, U3, U4, U5, not deltas. So again, you can see here, the aircraft is just here at trimmed, which is negative 10.2 degrees. When we introduce that positive 10 degree elevator deflection, that's a positive 10 from trim. So really the elevator here goes to negative 0.2 degrees, right? And then it goes down to negative 22.2, and then finally back to negative 10.2 degrees. So again, this is now working. We have the equivalent inputs to both the linear and the nonlinear system, and as such, we should be able to see roughly equivalent behavior. And look at this, it does seem to work, right? You can now see that the nonlinear and the linear models have roughly equivalent responses to that elevator doublet, right? And again, just to exercise fully, maybe what we should do is let's have a non-zero initial condition. So let's switch this now to, I don't know, how about here, I have this other condition I call initial condition 1, where here I'm turning off the elevator doublet. You can see right here, so the doublet magnitude is 0. So again, let's go with 0 inputs to both systems, or I guess we should be careful how we word that. 0 inputs to the linear system and trim control inputs to the nonlinear system, right? That's effectively what we're simulating here, right? And now let's make perturbations in all the states, right? So here's your all these have some non-zero, well, I guess except for this last one down here, still has a 0 perturbation, but that's okay. But again, we simulate the linear and the nonlinear using the appropriate techniques, and now even though we have this non-zero initial condition, let's take a look at the outputs, and look at that. And they still seem reasonable, right? They still seem to quasi-match up. So again, this is just a quick discussion, I think, on how we should be intelligently translating the inputs, outputs, and initial conditions between those linear and nonlinear dynamic systems. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. And speaking of the new videos, they come out every Monday, so I hope we'll catch you at one of these future talks. Lastly, if you're interested, you can support the channel via Patreon. I'll leave a link to that. The nice thing about the Patreon method is that we use 100% of the proceeds that the channel receives via Patreon, and we direct that towards STEM, science, engineering, and adventure activities for K through 12 young adults. So, like I said, with that being said, this is a good spot to leave it. I think I'll sign off, and I hope to catch you in the future. Bye.